When a star of 8 to 20 solar masses dies, it does so with a bang, a supernova. When it's all over, there will be a few octillion tons of superheated plasma expanding away from the explosion site at a rate that is a small fraction of the speed of light, a ton of energy released in the form of light and neutrinos, and a peculiar little ball of quantum nastiness in the center that is almost entirely made up of neutrons. It's okay if everything appears a little strange to you because the characteristics of this neutron star are almost as peculiar as they come in the cosmos. Astronomers even briefly questioned whether aliens were actually responsible for what they were observing. This is your host Yash Verma from Yverse. If you enjoyed the video, please give it a quick like, subscribe, and hit the notification bell icon if you want to watch more content. Let's set the stage. Imagine the core of a high-mass star as it nears the end of its life. In its last moments, it was fusing silicon and iron just a few milliseconds ago, but now it is being crushed by the gravity of its own enormous mass. Although the collapse only lasts a fraction of a second, a lot really happens during that brief period of time. Because electrons fiercely resist being squeezed together, a rule of quantum mechanics states that the center of lower mass stars is supported by electron degeneracy pressure. If the core has a mass more than 1.4 times the mass of the Sun, even electron degeneracy is unable to stop the collapse. It's simply too much weight to sustain, and the collapse keeps happening. Protons, electrons, and other subatomic particles smash together at these extreme pressures, merging to form neutrons as a result, and practically all of them experience this. The core basically becomes a ball of neutrons when it shrinks to a diameter of just about 20 miles, with a few protons and electrons surviving here and there, and a crust of ordinary but extremely compressed matter on top. When this happens, another effect occurs: neutron degeneracy. Neutrons are much more resistant to being pushed too closely together like electrons are, but this time the pressure is much stronger than it is for electrons. The collapse hits a wall and stops if the core is smaller than around 2.8 times the mass of the Sun. This causes a massive shockwave to be produced, which, coupled with a flood of neutrinos, which again are very energetic subatomic particles, explodes outwards, blowing up the star. After the figurative smoke clears, what's left of the core is a neutron star, one of the strangest objects in the universe. Such a star would be absurdly bizarre or simply outrageous. It would be more massive than the entire Sun and fit into a sphere only 20 miles in diameter. Let's pause right there for a moment to give that some thought. The Sun is 300,000 times more massive than the Earth. Think about squeezing everything into the ball the size of a small metropolis. The Earth contains everything and everyone we know, love, and cherish: our collective history, our present, our fantastic future. Imagine something that can hold 300,000 times that volume and fit that into a small city. Is that too much for your mind to handle? Is that too complicated? Okay, consider this. You are primarily empty space. Every atom in your body contains a nucleus that is composed of closely spaced neutrons and protons with spinning electrons surrounding them. If you could magnify an atom to be 100 meters across, the nucleus would be roughly the size of a marble. Imagine all of that empty space between the nucleus and the electrons. That is a normal atom. However, in a neutron star, neutrons would occupy every available space, all of it. The neutron star is filled with mass down to the size of an atomic nucleus in every nook and cranny. This is what gives a neutron star its explosive and powerful ability. Take a deep breath because I'm about to bombard you with a lot of numbers and you might want to take a seat. Neutron stars have absurdly high densities. Neutronium, the substance that makes up neutron stars, which is made up of just neutrons, weighs around 400 million tons per cubic centimeter. Do you need some context for that figure? Well, approximately speaking, That is the combined mass of every car and truck in the United States. Imagine a few 100 million cars being squashed until they all fit within this six-sided die. That is neutronium. Because of its extreme density, ordinary matter appears to it as a slightly contaminated vacuum. If you place neutronium on the ground, it would fall right through the surface of the planet. Any object that is that dense has a strong gravitational pull. You would obviously be dead if you were on the surface of a neutron star, like instantly thin to only a few atoms in thickness. And the reason for that is that the surface gravity of a normal neutron star is 100 billion times greater than that of Earth. On Earth, I weigh around 230 pounds, a large guy, despite having a mass of about 105 kgs. I would weigh 18 trillion pounds on a neutron star. That is 24,000 times the weight of the Empire State Building. But hold on, there's more. If you shrink the size of a spinning object, like a neutron star, the spin would increase. The typical illustration that goes along with this is imagine an ice skater who kind of draws in their arms and accelerates their rotation till they become a blur. The star's core experiences the same conditions when it disintegrates into a neutron star. Before the explosion, it might have had a very slow spin that took weeks to complete. However, that rotation will significantly increase when it shrinks to a size of only 20 miles wide and transforms into a neutron star. A newly formed neutron star may spin multiple times per second. The magnetic field also gets stronger. The overall magnetic strength of a star like the Sun is similar to that of the Earth. A neutron star's magnetic field, however, can easily be several trillion times stronger than the Sun when its core collapses, causing the field strength to soar. That is powerful enough to cancel your credit card from 100,000 miles away. See, that's absurd. These are all mind-blowing characteristics, but are they real? Could such a thing actually exist? Yes, absolutely. In 1965, the first neutron star was discovered. It wasn't considered to be a neutron star at the time, and it wasn't really being acknowledged as such for what it was. However, just a few years later, another one was discovered, and this time it was accurately classified as a neutron star, but then strange things started to happen. In 1967, graduate student Jocelyn Bell was working on constructing a radio telescope. She, along with her team, were unable to eliminate this one persistent noise in their data, and Bell investigated it day and night before realizing that the pattern wasn't related to an issue with their data, but rather the issue came from an actual celestial object. She had stumbled upon the very first pulsar. You may wonder what a pulsar is. Neutron stars are pulsars. To put it simply, because of their quick rotation and extraordinarily powerful magnetic fields, they shoot out twin beams of magnetic energy that resemble lighthouse beams as they travel away from the star. As the star rotates, the beams move around and are visible as pulses or blips of increased brightness from Earth. This pulse can be seen in radio waves, X-rays, and visible light. Because the spin of a neutron star is so steady, these pulses act like an extremely accurate cosmic clock. This object was given half-jokingly the name and the designation of LGM-1, Little Green Man 1, in 1967, since no one could actually believe a natural object could behave like this. We currently know of nearly 1,000 pulsars in just our galaxy alone, and we know that they are the relic cores of huge stars that have exploded in our past. Some spins last for several seconds or even several minutes. Some are orbited by another star in a binary system, a system of two stars. In this case, the neutron star can actually consume material from the other star if they're close enough to one another. This enhances the pulsar spin, and we are aware of a few that rotate at extraordinarily high speeds. Some spin several hundred times each second, which are known as millisecond pulsars, and despite their extremely high gravity, if they rotated much faster, the centrifugal force would rip them apart. A pulsar can continue to be a powerful force even after 1,000 years. The Crab Nebula contains a pulsar in its center, which is the remains of the star that exploded and left behind that supernova remnant. The pulsar itself powers a significant portion of the light that the nebula produces. The nebula is energized by its powerful production, which makes it sparkle brilliantly even after a millennium. I'm telling you, the back of my neck starts to rise up in excitement and just in pure terrifying awe when I think of neutron stars. And I haven't even mentioned magnetars yet. There's more to neutron stars than just strange neutron-filled balls. They have a crust that is only a few inches thick and is formed of extremely compressed but largely normal matter that has been forced into a stable crystal structure. This crystalline crust is pierced by the star's magnetic field, which extends for quite a distance. The magnetic field in some neutron stars is significantly stronger than typical, and get this, can be a quadrillion times stronger than the sun's. The term magnetars is used to describe these extremely powerful neutron stars. However, they are relatively uncommon. Only 10% of neutron stars begin life as magnetars and have very brief lives. Because of how powerful the magnetic field is, it slows down the neutron star's spin like a car's brakes. And as the star slows, the magnetic field, which is fueled by the spin, becomes weaker. But while they're around, magnetars are some of the most magnetic objects in the universe. And with tremendous power comes enormous responsibility, if it is your job to be one of the universe's most terrifying things. Why? Because the magnetic field and crust of a neutron star are bound together, changes to one have an impact on the other. The star's powerful gravity and quick rotation put a tremendous pressure on the star's crust, and if the structure slips, it can snap and cause a starquake, like an earthquake, but just a wee bit stronger. When the Earth's crust changes and cracks during an earthquake, enormous amounts of energy are produced. This energy is sufficient to obliterate buildings and figuratively move mountains. However, this effect is greatly enhanced in neutron stars. Keep in mind that the gravity is very strong and that the crust is incredibly dense. The amount of energy released if the crust stretches and breaks, dropping just 1 inch, is unfathomably large. An enormous explosion caused the crust to shake as this energy is released. The magnetic field responds as a result of this shaking. Poorly. When the sun's magnetic field has a temper tantrum, we get a solar flare, which can be as powerful as billions of nuclear bombs. That is dwarfed into nothing by a magnetar flare. Compared to a solar flare, it may be trillions of times stronger. A magnetar has the ability to emit as much energy in a split second as the sun does in 250,000 years. Astronomers were shocked in 2004 when a powerful X-ray burst and blasted onto orbiting satellites. Even though it wasn't even facing at the source at the time, one of these satellites, called Swift, actually had its X-ray sensor saturated with radiation. The X-rays were so intense that they actually passed straight through the side of the satellite, temporarily blinding Swift, which was intended to detect strong X-ray sources. That's funny, right? The consequences of this X-ray burst were astounding, and it was shortly discovered that the source was a magnetar known as SGR 1806-20. In fact, it ionized a portion of the high atmosphere and constricted the Earth's magnetic field. And oh, I almost forgot to mention that this magnetar is located 50,000 light years away. That's halfway through the Milky Way galaxy. That's amazing. And even though SGR 1806-20 magnetar is at a distance of 300 quadrillion miles, its effects were felt more strongly than a powerful flare from the sun. The good news is that there are probably less than a dozen magnetars like this one in our galaxy. Catastrophic explosions like the one in 2004 are additionally very uncommon and very rare. And we would have noticed it if it had occurred at any other point in the last 40 years or so. It's also pretty fascinating that we have the technology and the astronomical satellites in space that could examine the Earth. Since neutron stars were initially discovered, we have learned a lot about them, but there's still plenty that we don't know. And every single time that we learn more, we discover that they're even crazier than we originally thought. Despite all of that, they are hardly by any means the most unusual objects in the universe. The other type of object generated in a supernova, a black hole, is quite securely holding onto that position. Stay tuned if you want to learn more.